Welcome to the Relatorium, or I say good afternoon. I keep saying good morning because I'm in California time, but wherever you are, welcome to another edition of the Relatorium seminar. We're very happy today to host Tai-Danae Bradley, who will talk to us about quantum encoding and some new work she's been doing in the field. Take it away.
Yeah, thank you, Ted, and thanks for everyone for joining. I'm going to try to pull up my slides now. So can you see it okay? Okay, great. Yes, so I'm going to share with you some work that's a little newer for me. So this is a project that I started a couple of years ago with collaborators at MIT and Deloitte. So I don't know if you know, but Deloitte has a quantum research group, Deloitte, the consulting company. So this has been kind of fun for me. It's a little bit different than research that I usually talk about, as I was telling Ted before we got started. I'm going to keep this at a very high level. So this will not really be a very technical talk, but I just kind of want to give you a bird's eye view of kind of the confluence of ideas here. And so, of course, at any time, if you have questions,
Yes,
please
in
ask.
fact, I was just going to suggest, as Tai-Danae knows us very well for a while, the spirit of the Relatorium is to engage in conversation. So raise your hand. Irfan will be monitoring. Well, anyone really can be monitoring. And I will be interrupting sometimes if you end up going too long or if I end up, not feeling like we have everyone. But, let's keep it informal. Thanks, Tai-Danae. Go on.
Yes, yes, I like informal. So thank you. And I also appreciate this seminar and the work y'all have been doing. So thank you for the invitation to be here. Okay, so basically, I'm gonna share with you a small problem in the field of quantum machine learning, which I don't want to assume that everyone listening already knows what that is. So I will give kind of a brief introduction in a little bit. But there's one particular problem that we became interested in this field, and we realized that that problem can sort of be translated into the language of category theory. Um, it's not super complex or sophisticated, but there's actually a natural way to think of this category theoretically. And we thought maybe that might be advantageous because when you start to think of it from a more formal mathematical perspective, maybe that might open up a new toolbox that folks in the field of QML, quantum machine learning, didn't know existed or hadn't really tapped into yet. And so our hope was to kind of see, hey, maybe if we look at this problem from a different perspective, one that a mathematician might view it from, maybe that might shed light on other ways to tackle this problem that's going on. But because this is new, the field itself is relatively new. The work I'm going to share with you is relatively new. I don't have a status update for you. Like, did we accomplish the mission? Okay, so this talk is just, I'm going to describe for you the sort of problem and how to think of it category theoretically. And then, time will tell whether this is going to be something that can provide concrete sort of engineering perspectives for this problem. So this is joint work with Arthur Parsignat at MIT, Andrew Vlasic at Deloitte, and An Pham, who's now at GNQ. So this is a paper that was in Physical Review. It came out last year under their perspective papers category. So again, that shows you kind of the flavor of the conversation we'll have today. This is not so much research, but it's just we're offering a perspective. Hey, you guys are kind of coming from the physics engineering background. We're coming from a category theoretical background. Here's how we think of things. Is that helpful to you guys? So that's kind of where we're coming from. So, okay, what is QML? So quantum machine learning has been around since 2013 or so, and it explores whether quantum computers, and I'll say a little more about quantum computers in a second, offer advantages for solving real-world problems in machine learning. Now, initially, maybe there was this idea that, hey, we have a lot of tools and ideas from classical machine learning in terms of training and algorithms. Maybe we just kind of port those ideas over and see what happens. And so the field tried that, and they're like, actually, that's not super useful. So you can't just do that and expect smooth sailing. And so over the past few years, there have been calls for new approaches that are more methodical, that are a little more insightful, and try to find ways to harness the things that quantum computers are good at. So rather than just kind of blindly applying machine learning ideas. And so I like this quote that came out from a group at Xanadu: until quantum computers become available to do large-scale benchmarks, asking more fundamental questions may be a good use of our time, but maybe asking more fundamental questions isn't always, super sexy. So it requires a little courage.
Um,
And of course, from
can I
math,
ask,
yeah, yeah.
can I ask a question? What comes to my mind is, for example, attempts to create quantum versions of essentially, search algorithms, optimization algorithms that had been underlying much of ML in the past. And is this suggestion essentially saying maybe there's something more native within the quantum realm rather than just porting and quantifying or quantizing existing search algorithms?
Yes, yes. I think that's part of the trend that's happening now. Even earlier than that, the idea is just kind of, well, I'll get into this in a little bit, but some of these early ideas and where this talk sits in is you have a neural network and you want to learn the parameters so that it gives you the right function that you're looking for. And so particular class of quantum circuits are very similar to that. Um, they're called variational quantum algorithms. And some of the techniques, because they're so parallel, you kind of say, hey, we do this thing in machine learning. Let's just try that over here. And that's an even more sort of bare bones way of thinking of it. And that's kind of where some of the roadblocks had come in years past. And now, more recently, even this past year, there was a conference in Singapore, Quantum Technologies and Machine Learning. And the trend now in 2025 is thinking back to sort of these original quantum algorithms. What is it that quantum computers offer? Like they're harnessing structures somehow. Like let's think more carefully about that. Things like quantum Fourier transform and other things. And so that's kind of the trend more recently. So I'm kind of rewinding back a little bit, and I want to think about this sort of variational idea that's closer to neural networks. Um, so I think this is familiar, but I just, for the sake of completeness, I just want to mention that quantum computers, this is a piece of hardware that stores and processes and shares information that's fundamentally different than classical computers. And so, of course, instead of, transistors on your silicon chip, which has, current flowing or not flowing, so that's essentially a bit, a 0 or a 1. Um, you're processing and storing information on individual atoms or artificial atoms, like superconducting qubits or similar. So these are quantum bits. And the whole point, of course, is that physics at the atomic scale is different than physics at the macroscopic scale. So maybe there's things you could do on a quantum computer with particular problems that you may not be able to do on a classical computer. But if you're going to even explore this in the context of machine learning for classical data, one of the first questions you have to ask is, how do I even encode that data onto my quantum computer? And I'm gonna like, what does that even look like physically in a lab? So I'm gonna explain that a little later on. But here's the point. It turns out there are a lot of ways to do this. And it is not clear which is the best way for a given data set and a given machine learning task. And that's kind of where we're coming from.
So in risking possibly, kind of having this comment sort of go in a different direction than where you want to go, and please shut it down if that's the case. I wonder if or how this might relate to thinking about quantum computing as essentially physics simulators, like simulating physical problems. So where, in other words, the question becomes, how do we take a computational problem and represent it as a physical problem, and then have the quantum infrastructure essentially play out the physics Does that at all resonate, or is it, because I know that some people have thought about that?
Yes, yes, absolutely. So I think that falls, so there's kind of two categories in which you can use quantum computers for machine learning. There's quantum computing for physics, and then there's quantum computing for classical data. I mean, quantum machine learning encompasses both of those things. I will be talking about the second category, quantum machine learning for classical data, things like images, time series data, things like that. Um, the the crossover between the two, I'm sure there's some similarities to a certain point. I think the ideas that I'll be talking about today really lie strictly in the second category. And in fact, I appreciate this question in the chat. Do we even know if there is a best way for any specific task? And the answer is no. The answer is no, because there's different, and I'll get into this later, there's different pros and cons that you have to weigh and then make that decision. Like, what do you want to optimize for example? But I think that at least having a framework in which you can think about this methodically is helpful. And even that is not quite clear yet because the field is so young. Yeah. So I wanna spend some time opening this problem a little bit. So I really want to narrow down on like what is the math that we're asking behind this thing I'm calling open problem in a box. How do you encode data, classical data onto a quantum computer? But what is that in terms of math? Okay. So to answer that, I just want to do like, so we have this in our mind. I just want to recall what it's like in regular deep learning, classical deep learning. So basically, it starts with a function. I'm really simplifying this, but I think that's okay here in this conversation. I just want to kind of keep it high level. So let's just suppose we want to label some data. So imagine you have a set of some data, a data set X, maybe elements in X are like images or something you want to classify. And Y is your output set. Maybe these are just like labels, like cat or dog, +1 or -1, whatever. And the whole point is you want to find a function that correctly assigns a label to a given data, a given image, for example. Okay, so how do you do this? Well, for simplicity, let's just say our sets are Euclidean space. The idea in deep learning is that you kind of want to think of your function as being built up as a composition of smaller functions, where the smaller functions involve some weight matrices, M, and maybe a bias vector and some nonlinear activation function, A. And the goal of the learning algorithm is to learn the parameters, the entries, these numbers and these functions, so that when you compose them, you get something that's really close to the correct labeling, right? That's correct to the close ideal function that you want. And so you have to learn the parameters. So that's classical deep learning. And the point I'm trying to convey is that this particular paradigm of quantum machine learning that I kind of hinted at earlier, variational quantum learning, quantum circuits, are very similar. So in quantum machine learning,
Well, I was just going to say, I mean, in the compositional framework that you raised, I mean, obviously, currently the way you showed it, it was each of the components was linear. So obviously the composition of linear functions would be linear. I suppose one of the components, so either we can add, either we can think about in the context of classical ML, particular parametric families of nonlinearities like radial basis functions or other kinds of things. But separately from that, there's the question of dimensionality, right? Like, I mean, in a sufficiently large space, everything could look linear, Do you see what I'm saying? Like you can encode the nonlinearities as part of your dimensions. So is this part of the thinking?
So yeah, in this picture here, there's definitely the Fi are not linear because I'm starting off linear. I have my input vector and I have some weight matrix, but then this A thing, this
So A
A,
is a function, it's not a scalar.
yeah, A is a
Okay,
function,
okay.
like a
Cool.
ReLU or something like that. Yeah, thank you. So this is not linear, so it's very messy, and so it's not straightforward linear algebra, but then that's where the nice parts of deep learning come in. But to your point, things are linear in the quantum version, but it's harder because you're dealing with actual physics here, and I'm going to get to that in a second. But under, the sort of goal is the same. I have my same data set. Maybe X is a set of pictures or something in classical data I'm interested in. Labeling Y is my output set of labels. Now, how do I understand this function? Okay, on a quantum computer. First of all, I have to encode, let's say, my image onto a collection of qubits, onto my quantum system. I drew qubits as black dots. You can think of them as something like atoms. These are individual atoms, maybe that have been ionized. So a type of qubit is called a trapped ion. So it's an atom that either lost an electron or has an electron. Or, these could be photons or superconducting qubits or neutral atoms. So there's a lot of different modalities here. But the idea is you take your data, a piece of data like an image, you somehow encode it onto your physical quantum system. Then you want to manipulate that quantum system. If these are ions, say, you sort of hit them with laser pulses with different frequencies and different time durations so that you manipulate the state of these ions, these qubits, so that when you make a measurement means like you shine a laser and maybe one of your qubits, your ions, fluoresces or it doesn't fluoresce. And that's going to be like, that's a cat or a dog. I'm going to say that's my +1 label or my -1 label. And the whole part of the learning algorithm is you want to find what are the analogs of the parameters now. They're going to correspond to physical characteristics like the time duration of the laser pulse or the frequency, like I mentioned earlier, so that I change the state of the system so that when I measure it, I get a response that I can identify as a label, like a yes or no, a label to is this a picture of this or that. That's kind of the high level version of the physics, but we just talked about this is like there's linearities here. So that means I need to translate this to linear algebra. So let me translate this picture to linear algebra by saying mathematically what a qubit is. And I know this is going to be a review for some people, but just to kind of make sure we're all on the same page, I want to re-describe this picture mathematically. To do that, let me just say, what is a qubit? Okay, like I just kind of said, qubits are physical quantum objects with two possible states. And the example I really like to think about, because it's kind of simple and you can hang your hat on it, is an ion whose, let's say it has an extra electron. Either that electron is close to the nucleus or far away. And that corresponds to two different energy levels. So like in classical computing, you have like a transistor with current flowing or not flowing. That's like a 0 or a 1. In quantum computing, you have an ion whose electron is close or far, and that means it has two different energy levels that you can observe, and that's like your 0 or 1. Mathematically, though, that's the physics. Mathematically, the state of such a thing is represented by a unit vector in C2. Two-dimensional complex Hilbert space. So here's my unit vector where the alpha-1 and alpha-2 are like probability amplitudes that I'm going to see two different energy levels. So the modulus squareds are the probabilities that I observe the energy is this number or that number. So that's if I have one qubit. One qubit corresponds to one vector in C2. But what if I have n, capital N qubits? Then that corresponds to, I basically take the tensor product of C2, one for each different particle, one for each different qubit. So I have a vector with 2 to the n entries, but it's a unit vector again. So a quantum state is the unit vector in complex Hilbert space. Question?
Well, I don't know if there are any questions, but I do want to point out this is a big sort of point of contention. So please, I want to invite questions. I think one way to understand the exponential nature of the indexing here is that, you know, each qubit dimension, like the two components of each qubit, essentially, you know, you're using them as binary basis for the indexing in the tensor product space. Irfan.
Yeah, so did you say that the alpha 1 squared plus alpha 2 squared represents the energy of the particle, or did I misheard something?
Yeah, no, they're not energies. The alpha 1 modulus squared, um, because alpha 1 modulus squared and alpha 2 modulus squared, they add up to 1. Think of those numbers as probabilities. So
Okay,
alpha 1 squared
right.
is the probability that the energy level is this number, and alpha 2 squared is the probability that the energy is this other number.
I see. Okay, good.
What
Thanks.
are those numbers? Yeah, that's not on the slide. You know, I didn't put that. I didn't even describe that on the slide. So that's why that was confusing.
So practically, when we imagine a large number of particles, I would imagine that those numbers would be modeled by something random or something like that, like some random variables.
Um, I mean, yes. So in quantum, your system is doing something, and when you make an observation and you say, okay, here's what's going on here, um, the answer can be given only in terms of probabilities, and that's a key feature of quantum physics. So when you're talking
Right.
about position or momentum or energy levels or something, you do a lot of experiments, and then you say, okay, on average, here's what we're observing. And those numbers or those statistics are what are encoded in this column vector, but you can't quite look at the actual entries and just read it off. You have to take this modulus squared operation
And
to get the
that's
probabilities that you are observing in particular.
Irfan, think of the qubits, the n qubits, when you collapse them, when you actually measure them, right? Each one will be 0 or 1. So eventually you create in binary a number between 0 and 2 to the n minus 1. And the alphas here represent the probability that you get that number. The alpha squareds represent the probability that you get that number at the end when it collapses.
So sorry, what is either 0 or 1?
So think of, I'm saying, think of it. It's an analogy. Think of each qubit. It's not sufficient, but think of each qubit as potentially being 0 or 1. Obviously, in reality, it's a vector. It's a two-dimensional complex vector. But think of it as when it collapses, it's going to become 0 or 1 in a classical sense. And so since you have n of them, you will have simultaneously n zeros or ones. In other words, you're encoding a number between 1 and 2 to the n, right? Or 0 and 2 to the n minus 1. So these alpha squareds are like the probabilities that in the end, when you do measure and collapse it, you will get one of those numbers.
it's, as I understand it, Tai-Danae, that each alpha j is a wave function. So because the magnitude squared is the probability for that qubit. Is that right?
I think the term, so I think the quantum wave function is analogous to the entire state vector, but
Okay.
when you take the modulus squared of the sort of terms that make up the quantum wave function, those are my alpha j's here squared.
Okay. And then it might be helpful to for other people in the audience to clarify tensor products, because there's a difference between tensor products and direct products usually, and it depends on the category. So it might be helpful to
Thank you.
explain the difference between those.
Yes, thank you so much for that suggestion. Okay, the tensor product operation, I wish I could draw on my slide, but I can't. I'm gonna, forgive me for how simple this construction is gonna be. I'm just gonna tell you how to take the tensor product of two column vectors and freshman linear algebra language, okay? So imagine I have a column vector with two entries let's just say real numbers, okay? We're going to keep it really simple. And imagine I have a column vector with 3 entries. You guys can see it, okay? If I take the direct sum operation, I take the direct sum of 2 vector spaces, what I'm getting is essentially like kind of stacking the vectors on top of each other. So now I have a column vector of 5 entries. This is very simple. Okay, it's just kind of like I'm taking 2 systems and I'm juxtaposing them side by side, but they're not mixing. They're just like they were separate and now they're together. The tensor product is different. If I take the tensor product of a vector with 2 entries and a vector with 3 entries, I'm gonna get a vector with
6 entries.
6 entries. How do I do that? I take the first entry of the first vector and I multiply every entry of the other vector by that. Does that make sense? So this guy times the first, the third, the second. The first, the second, the third. And then I do the same thing with the second entry in my 2 by 1 vector. I then multiply that by everything. So it's like you're looking at all possible interactions between the 2 systems. So the direct sum gives you a vector of length 2 plus 3. The tensor product gives you a vector of dimension 2 times 3. So the tensor product is basically saying, okay, I have these systems and I want to know every possible interaction. It's like a complete graph or something, and the direct sum is just like taking the disjoint union of 2 graphs. You just stack them side by side. Yeah, I really appreciate that question. So when you see this tensor product symbol below, that's kind of what that's alluding to. Yeah.
I would have a small question. It's kind of stepping back from the mathematics, but I was curious if you could provide a bit more information about the motivation for why we would want to do a machine learning on a quantum computer, because the example you provided with the cats and dogs, to me, all this information is discrete and there is no benefit in my mind from using a quantum computer. And in the end, the labels, they are also, I'm assuming, one-hot vectors. So it all seems very discrete, very classical. So what are the benefits that we're hoping to get from doing this on a quantum computer? Is it just going to be faster, or is it going to allow us to work with different kinds of data that we cannot work with on classical computers?
I love this question and I appreciate it. So let me say the field of quantum machine learning, which I am not a part of, so I don't want to misrepresent them well. As you know, my background is in math, but I've been had the pleasant experience of kind of learning about this and working with others. So the field of quantum machine learning is not just this. So as Ted was kind of asking or making the point earlier, there's QML for physics data, and maybe that makes more sense because you're simulating physical systems on physical systems. But at the same time, I think it's like an interesting question to ask. Is there any advantage over here with QML for classical data? I mean, maybe your intuition is no, but maybe your intuition is, hey, we don't know until we try and at least investigate this and find out where the problems are. So that's kind of where I'm coming from now. That's great.
Put it differently, essentially any classical algorithm can be described also in terms of linear algebra. And in this case, you have other primitive matrices. And because this linear algebra is a vector space over the complex, you might be able to do things more efficiently in principle, right? So that's how I see it anyway.
Yeah, and another thing that comes to mind as we're talking, there's analyses that you can do in your classical machine learning algorithms. Maybe you want to look under the hood and see how your neural network works. Maybe you want to understand what the algorithm is doing from a mathematical perspective. You might think images are like easy to talk about because, we have convolutional neural networks or something from a long time ago. But even in images, you have interesting information theoretic structure like mutual information among pixels, and maybe that's being learned by your algorithm somewhere. Well, quantum physics has an analogous concept called entanglement. But in quantum computers, harness entanglement in a way that you can't with a classical algorithm because entanglement is not a classical concept. So even asking a simple question like that, like, hey, maybe there's information in classical data that a quantum probabilistic perspective could lend additional insight to. Maybe that can allow us to approach things in a way we hadn't thought before, or that provides clarity to the problem that we didn't have before because we never even thought to think in this direction. So I think even from a research perspective, it's just curious, right? But then of course there's the practical thing, like, why would we do that when we have, like, amazing computers right now? But
I
researchers.
think it's worth making the point here. It's almost like a rethinking of a theory of computation.
Yeah.
In fact, nothing that you said so far is quantum, right? Except for the fact that you say c squared here. I mean, if it could have been like, r squared, or even r to the fourth, like we can consider the components as not being complex numbers, but being, real and imaginary. It's just a number of, it's in high enough vector space, basically.
Mhm.
I think, so the question of entanglement as well, I think, in my opinion, I've always minded that it's become this sort of surrogate for what is magical about quantum, when in reality, the thing about that makes it especially quantum is that there are one-off physically accessible operations that can bring it about, whereas it's a phenomenon we can describe here just as well. For example, entanglement, the phenomenon of entanglement simply means that as n increases, the vast majority of states in this space are not in fact tensor products themselves. In other words, the space itself, most of the vectors are not accessible as tensor products of simpler things. They are just entangled. Whereas the ones, this is a dimensionality argument, that the linear subspaces that are accessible as tensor products of simpler things are vanishing as n increases, a vanishing portion of them. So we could describe it classically as well. The problem is that we would have to do an exponential number of operations to do that. Whereas in a quantum system, if we have access to primitive matrices of the large size that can actually operate directly and move, entangle things and disentangle things in one-offs, right? We're taking advantage of a resource that nature has given us to do a computation that otherwise we would never have thought to do because it would be too unwieldy to do. So it's a question almost of encoding, like you're seeing your problem, which seems complicated in a low enough dimensionality, being put in a vaster, much bigger dimensionality where it can essentially be linearized. I mean, which is, I don't know. I mean, that's at the heart in my mind of why quantum computation might actually work in the cases where we can use primitive gates to these huge matrices, basically, to do the effect in few steps.
So I'd like to ask a question that it really is a question to both Ted and Tai-Danae about this. So Tai-Danae, you said that entanglement is a quantum phenomenon, but not a classical phenomenon. So this question I'll ask will partly ask you to kind of address a sort of pushback on that. And then Ted, the high dimensionality, I think this question will also kind of push back on the idea that it has to do with dimensionality. And here's the reason. I've often seen speakers describe entanglement with what I would consider a classical system, even though it seems like historically the notion of quantum entanglement has come out of looking at quantum size systems like particles. The example that I'm talking about is two people, say Bob and Alice, are given envelopes, and they know that they either have a 1 or a 0 written on the piece of paper in the envelope. And they are far apart from each other. And they also know that that one of the pieces of paper has a 1 on it and the other one has a 0 on it. But they don't know which until they open the envelopes. And as soon as Alice opens her envelope, she knows Bob has the other number. And that's what I've seen as a description of entanglement. And I would call that a classical system because there's nothing tiny about it. It's just information theoretic and correlation. You know that these two envelopes are correlated. You know how they're correlated. And it has nothing to do with dimension as far as I can tell either. It's just a very simple system in that sense. So that's, I've always been concerned about the explanations that seem to suggest that that entanglement itself is specifically a quantum phenomenon. It was discovered whenever people were looking at quantum phenomena.
Tai-Danae take this. Do you want to say something about that?
I have an idea, but I was trying to find a concise way to say it, and I don't have that yet. So Ted, feel free to go first.
So yeah, this comes up a lot, obviously among my students in my class, and it's a big learning goal towards the end of the class to kind of get there. You know, you get to there slowly. First, you start with qubits, and I think at the level exactly of what Tai-Danae is doing now, she's trying to show us first that qubits can do everything that classical bits can do. You know, in other words, we can do the encoding of the classical states into this. So there's obviously nothing new here. But eventually, entanglement really comes about when we're interacting qubits with one another. One way to say what happens is that the complex number, the fact that these are complex numbers, so they live in the block sphere. The first statement says that they live basically in a three-dimensional submanifold in 4 dimensions, right? Like a sphere, a three-dimensional sphere in 4 dimensions. And it turns out that, you know, for an individual, this is a postulate of quantum mechanics, of this formalism of quantum mechanics, and it's one that is born out of the data, that actually of these 3 degrees of freedom, one is always unobservable. There's an unobservable phase, an angle that is unobservable for individual qubits. All you can ever observe is the difference of phases when 2 qubits interact. And this gives, if you will, the ability for qubits to interact in ways that are not reducible to classical ways of interaction. So the phenomenon you described, of course, you know, we've all heard that. That's not a good example because, sure, qubits can do that. And at that level of description, it would look analogous to what classical systems do. But qubits can also do other things, entangled qubits, I mean, can do other things that are not explainable probabilistically by, for example, the statement that they were either 0 or 1 to begin with. They themselves weren't 0 or 1. In fact, they weren't separated. In this case, that's what I meant by the entanglement. 2 qubits are entangled when they cannot, when their joint state in the, let's say if we have 2 qubits, they would be in a 4-dimensional complex, like you know, it would be C2 cross C2, right? So it would be a 4-dimensional complex vector space. Their state, well, which would be a vector in a 7-dimensional sphere in that, you know, in that 8-dimensional space, is not arrivable, it's not describable as a tensor product of 2 individual members of the block sphere, because those would be 6-dimensional. It would be 3 times 3, 6-dimensional, right? So most of the 7-dimensional space in which the 4 things can, in which the 2 qubit states could live, are not in fact tensor products. So you cannot say what part of that state is attributable to the 1 qubit or to the other qubit. They are just jointly one thing that happens to be in this joint state. So we misconstrue this because we say, well, but 1 qubit resides here, I have it in San Francisco, and the other qubit is in Rolla, let's say, with you. Well, that's just the physicality of it, which is, we're talking about information here. The information is in a state that cannot be, you know, assigned to a particular location. There are, of course, philosophical questions around what does this mean for locality and all that. This is beside the point here, right? But we're talking about the formalism. The formalism means that most of the states, as n increases, most of the information states are not separable to the individual components. I don't know if that helps.
Well, it sounds to me like and like you've got a beginning. You begin with the philosophical commitment to what Einstein called creepy action at a distance. That you're accepting it at the outset rather than taking it as uncertain whether that exists or not.
Well,
That's
personally,
what I think. That's what I think it sounds like. It might not be what you intend, but that's what it sounds like.
Personally, at what I've said, I don't do that in the sense that I'm taking a more epistemic view of things. This is a property of the story we tell, of the formalism we tell, right? But Daniel is right in the chat in pointing out that there are physical consequences of this, including Bell's inequalities. This is the actual way in which this is physically instantiated, the reason, the physical data-driven reason why the formalism has to encompass this, because there are measurements in these sort of Bell states, Bell type measurements, where the correlations between the measurements that you get are provably inaccessible to classical states. So if they were bits, in other words, they were 0 or 1 and the uncertainty was just that we didn't know, you could never get the correlations you would get. So they have to essentially themselves not be in a fixed state ahead of time of the measurement. So this is, I'm simplifying with this statement, work that has happened over, I don't know, 80 or 90 years and recently even won Nobel Prizes. So it's unfair to do that. But suffice it to say that I'm, as a mathematician, taking this as part of the formalism without wondering yet, temporarily for now, what can it mean? How can the universe actually be structured in this way that allows that to physically happen? But it does, apparently. So let's take advantage of it.
I'll have something to say about Bell's inequality, but I'll let Tai.
Yeah, sorry, we've really. I'm sorry.
We always co-opt the speakers.
I'm happy to be co-opted, so it's no problem. Maybe I'll just keep my answer short, or if we want to stay here for a while, that's fine. But look, I was going to give a not philosophical answer because it is a little hard for me to wrap my head around that. But I feel comfortable thinking about entanglement and making claims like it's a quantum thing when I think about the linear algebra that physicists in practice use to like work with entanglement. And I don't know a good way to say this. So can I just ask you, do you know, are you familiar with singular value decomposition?
Yes.
Okay. So let me say it like this. Look, I think you can see my mouse. So we have these particles, these dots, this quantum many-body system. And just imagine, you know, I color the left half blue and the right half red or something. And a natural question is, how much entanglement is there between the blue dots and the red dots, the blue particles and the red particles? Okay, that answer is a number. How do you compute that number? You look at this vector right here of 2 to the n entries. Okay, you reshape it into a matrix, which represents a linear transformation from the Hilbert space associated to the blue region to the Hilbert space associated to the red region, or whichever, red to blue, whichever. You can compute SVD on this matrix. When you compute the SVD, you get a diagonal matrix of singular values. And you can compute the Shannon entropy of those singular values, or maybe the square. I think it's the square of them. You take the square of them and you get a number. That number is called the entanglement entropy. And that is capturing, that's one measure of how much entanglement is between the two. So what is that? How does this, what does that have to do with classical stuff? Okay, imagine the classical version of a joint system. That's just a joint probability distribution. Imagine each of these dots was like a playing card, you know? And maybe I'm interested in 2 features of playing cards. Like they come in colors. Every card is, you know, black and it has a number, 3, red, 5, black, queen, red, whatever. So imagine now each of these entries, alpha 1s, are just the joint probabilities. The probability I have a black 1, the probability I have a black 2, the probability I have a black 3, and so forth. all of my cards. I can do this same process. Okay, I can compute SVD of that thing. Or I can pretend this is a quantum system and instead do something like I can massage this a little bit and maybe take the square root of each probability so it looks more like a normalized quantum factor and then do the same thing. And I'm claiming for you, I wrote about this in chapter 1 of my PhD thesis, so I feel very confident about this. If you do this same process, you will find that the left and right singular vectors for these two different scenarios, cards that I think about classically or cards that I kind of add a square root and treat like a quantum system, contain different information. There's actually a sense in which the quantum analog of a classical probability distribution contains information about these two subsystems, colors and numbers, that are inaccessible to you when you just do this the normal way. And the way to see that is a little bit like if you kind of look at marginal probabilities and you're like, okay, tell me everything I know about colors and tell me everything I know about numbers of the cards. Marginal probabilities tell you about those two systems separately, right? When think about computing marginal probability, you're literally summing over one of those subsystems. You're losing information.
Yeah.
But when you do this, yeah,
That's
Ted.
beautiful. In fact, your thesis, I'm glad you mentioned that because I've used reference to that chapter of your thesis
Yeah.
before with my students. It's a
Yeah.
really nice example. It basically goes to show that it goes beyond what is accessible to correlation. Correlation is a quadratic measure. It's almost like you can approach that by thinking of like contingent correlations, like almost like encoding if-then statements. If this is in this half of the thing, then and the other thing is in the other, but in ways that cannot be separated into just pairwise things.
Right. I love the way you described that. Thank you. So to summarize, because I know I don't want to leave everyone in the dust. When you do classical probability, you're basically dealing with sets. I have a set of stuff and they have probabilities on them. As you can see on this slide, quantum probability, quantum physics deals with linear algebra.
Mm-hmm.
But how do you get a vector space from a set? Just look at the vector space whose bases are the elements in the set. So there's a passage from classical to quantum is essentially a passage from mathematics on sets to mathematics in linear algebra. And as you can see, you feel intuitively that linear algebra is more roomy and there's a lot of structure. Like you can add things and multiply things and stretch things, right? That you cannot do with sets. So just intuitively from a high level, you might see that there's some things you can do in linear algebra that you can't do with sets. Analogously, there's some things you can do with quantum probabilities that you can't do with classical probabilities. There's this thing called entanglement that is mathematically a linear algebraic idea. It's like the rank of a particular matrix. And so that gives you information that you might not have at the set level. So that's how I could say confidently entanglement is the quantum thing. I was thinking only as a mathematician. I'm not too good at philosophy.
Right.
Well,
No.
so the thing about Bell's inequality is that I'm not only thinking about this philosophically, but also pedagogically. There are people teaching this stuff online who are considered top teachers and so forth. And to me, the idea of telling people that it's like Alice and Bob doing this stuff makes it sound like quantum mechanics is just classical mechanics, or may as well be classical mechanics, but talking about the information theoretic viewpoint. And then, and that's specifically for quantum encryption. I think that's where that example comes from. But then the point about Bell's inequality is that there are top science communicators, mathematics communicators who give discussions of Bell's inequality being an instance of essentially Venn diagram calculations. And one of them is on minute physics. And I saw that several years ago. And that's one of the I don't remember who gave the talk, but oh, it's 3 blue, 1 brown. So Grant Sanderson. And so that way of describing it seems to convey to the reader and the watcher of the video that it's just an example of set theory. It's an application of set theory. That may not be the correct way of interpreting it, but it's the way it comes across as far as I can tell. And so that's why I don't see that the discussion of Bell's inequality just bringing it up, Daniel, I don't see that it clears up the issue, because a lot of the ways of conveying Bell's inequality and what it has to do with things to people is classical. It's classical logic.
So it's the same kind of thing as what Tai-Danae was now describing. I mean, when Bell did it back in, you know, the 60s, it was brand new. And in fact, to be clear, he was a physicist. He wanted to demonstrate that this was doable in one step, essentially, like in you know, it was what we call in quantum information a feasible operation, right? A scalable operation, in terms of the physical substrate. Whereas what we're talking about now is an information operation in general, mathematically speaking, like a formalism, a mathematical formalism to demonstrate what that is more generally. So these analogies, these examples that Tai-Danae, for example, was talking about in probability, those are, you know, I think more accessible because they're more, they sort of don't have anything to do with quantum, right? But they're demonstrating they can only be instantiated, you know, in the physical world through quantum phenomena, because we have this, we're so lucky, I guess, that the universe has been made in this way that allows us to access this. I think, you know, in terms of the Bell's inequality, it's that a certain correlation, the correlation that we actually get in the data is simply not accessible as a correlation from any model of that would be classical. And that's provable. And I mean, so it's the kind of thing that that you do in classes, right? In quantum information classes. But finding simple, I mean, there's these impossible squares, for example, 3 by 3 impossible squares that can be solved with entanglement if you allow the states of the cells in the state in the, you know, in the square to be qubits rather than bits, right? Whether they're odd or even, and they're in some sort of superposition, which can be solved, and you can prove they're unsolvable classically because of conflicts, right? So this is like where the logic of the qubits essentially goes beyond classical logic of bits, because it can, in other words, that you can describe a state of the whole thing, of the whole 3 by 3, you know, square in that case, that is valid and solves the problem without ever being able to specify what each cell was for sure. Do you know what I mean? That, you know, in any, which is something we can't do classically, because classically the whole is made up of the individual parts, right? There's not that space of being entangled, of not being separable. Anyway,
we need to let Tai.
Yeah, sorry.
Make some more progress on what she was going to tell us today.
This is great. I don't even remember how we got here, but I think it's delightful. Okay, so let's see. I brought up this slide on qubits because I was kind of describing this paradigm for the machine learning part of a problem on a quantum computer. So the idea was you have a data set here. You want to encode it on your quantum system, then you want to manipulate that system so that when you measure it, the probabilities, the alphas that we talked about, are such that when you see an output, a particular output, that corresponds to a label, like either your ion fluoresces or it doesn't, and that lets you know that's a, you know, 1 or a -1, whatever. But I wanted to make that more mathematical. So I think now we can appreciate, I really, you know, my quantum system mathematically lives in a Hilbert space. And that idea of physically manipulating your system, the example I like to revisit is like, you know, pinging my system with laser pulses, those operations mathematically are represented by unitary operators. Why unitaries? Because they preserve inner products. So if I start with a unit vector, I end with a unit vector. So I'm maintaining a state. Technically speaking, these are like tensor compositions of tensor products of unitary operators. And that picture is called a quantum circuit, which looks a lot like a string diagram, right? Which we were talking about earlier. So,
just to say, compositions are just products, and tensor products are just compositions are products, and therefore they're like series operations, and right, and tensor products are parallel operations.
Perfect, exactly. Yep.
And the product you're talking about, Ted, is not direct product. It's multiplication of matrices.
Multiplication, yes, of matrices, yeah.
Yep. Thank you. That was great. And then the point is the machine learning happens there. You want to learn the parameters of your unitaries in these compositions of tensor products. Okay. What I wanted to say was the problem, the open problem is the first arrow, the first vertical arrow. So when I said, hey, what's the best way to input classical data? And as someone astutely pointed out, there's no one best way, but even how do you even, what framework do you even ask this question? What tools do you have to even analyze, under certain circumstances, what is a good choice? So by the way, this function, I want to emphasize this is a function that takes, an image and sends it to a quantum state, is sometimes called a feature map, an embedding, or an encoding. So when I say a quantum encoding, I am literally referring to this arrow, which I want to emphasize again, just to be really simple, is a function from a set to a Hilbert space. So it goes by different names in the literature, but I'll call it a quantum encoding. Now, I think it might be helpful if I give two examples, and this is actually going to go back to an earlier question about the actual physics. So suppose for simplicity, our set has a whole bunch of grayscale images, and let's just consider a 4x4 image. I just put some random pixel values there, grays and blacks and whites, 4x4, so this is actually manageable, okay? So let us think of a grayscale image as a column vector. So I'm just going to kind of snake around, and then write all of the pixel values where think of white. A white pixel corresponds to 0. A black pixel is the number 1. And then every shade of gray in between is some number between 0 and 1. So these values are the PIs. So I'm claiming we can get a quantum state from this. So here's a image. How do I get a quantum state? What's a quantum state? In this talk, it's a unit vector. So how do I get a unit vector from this?
You answer a bunch of yes/no questions. That's what each unit vector in your basis for your quantum, your orthonormal basis for your quantum. Actually, it's all the unit vectors on the sphere, but you reduce it to a basis, an orthonormal basis, and each of those represents a subspace where the answer to a yes/no question can essentially live.
Yes, yeah.
I'm being very, very loose with the word live there, but
no, that's good. Yeah. I can think of these standard basis vectors. I think you're talking about as a 1 with a bunch of zeros elsewhere.
Right.
Yeah. Yeah, those
each of those is a bra or a ket. I can't remember which.
Yeah. I was avoiding bras and kets to try to just keep it at, undergrad linear algebra. But in this case, here's a way we can think about getting a unit vector from this vector, just normalize it. So just divide it by this one, the square root of the sum of the squares of the entries. So you normalize it. This is a perfectly fine example of a unit vector of a quantum state. Even though it's simple, this has a name, it's called amplitude encoding. So this is a thing you can do. And you're like, okay, big deal. Let me tell you how to think of this physically. Okay, how does the physicist think of this? What we have just done, as elementary as it is, corresponds to a system of 4 qubits. Why? It's a 4 by 4 image. So this corresponds to a system of 4 qubits. Now remember, you guys remember the slide we camped on for a while? It had these alphas and you square them and you get probabilities. So I'm going to now tell you how to think of these PIs as probabilities, okay? PIs, the pixel values. So this corresponds to a system of 4 qubits. Again, I really like the trapped ion. It's just an atom with an electron. Now, depending on the state, the energy level of one of these atoms or ions, it will fluoresce or not fluoresce. Like it'll shine or not shine under a measurement, depending on its state. Well, I have 4 of them, each of them with 2 possibilities, fluoresce or not. So I have 2 to the 4 or 16 possible configurations that I could observe. Like this guy, it's like, think of them as light bulb. This light bulb is on or off, this one is on or off, this one is on or off, this one is on or off. So that's 16. And the point is the probability of each of those 16 configurations are the squares of the entries of that vector on the previous slide. So if you actually write this out, you'll see that the probability of seeing the first 3 ions dark and the last one fluoresce is the square of the second entry, P1 squared over M. The probability that all of them fluoresce is the square of the last entry, P15 squared over M, and so forth and so on. So I think that's...
Aren't they really the squares of the magnitudes? Because the P1 and Pn can be non-real numbers. Yeah.
Absolutely right. Yeah, so I put that in parentheses here. Technically, it's the modulus squared, but because our pixel values are real, okay, it just ends up being the square. But you're absolutely right. These are, in general, complex numbers. Okay, so that's just kind of how to think of something that's familiar to us, like an image, a grayscale image, as a quantum state. That is called amplitude encoding. You remember, I told you there's many other kinds of encodings. Let me just give you one more so you can see kind of the creativity here. This one is called angle encoding. Let's think of our same image, 4 by 4. But now what's going to happen is you assign each of the 16 pixels a particular vector, and then you take the tensor product of all of those vectors. So what vector is it? Well, you basically think of each pixel value as some angle of rotation in 2D. And so and you get a unit vector by taking sine and cosine of that pixel value times pi over 2. So P0 corresponds to this 2 by 2 vector. P1 corresponds to this 2 by 2 vector. You can check they're normalized. And if I take the tensor product of 2-dimensional unit vectors, I get another unit vector. So this indeed is a genuine quantum state. So I'm viewing, sort of not intuitively, physically, I'm viewing pixel values as angles of rotation. So what does this correspond to physically now, if you're interested? This now corresponds to a system of 16 qubits. Each pixel now is like corresponds to its own qubit. Just like before, let's just say they're trapped ions. Some will fluoresce or not, depending on their state. But now there's 2 to the 16, or 65,000 and some change, possible configurations. So if I make measurements, imagine I have 16 light bulbs, some are on, some are off. So what's the probability of each possible configuration? Okay, it's this thing. So I gave you a particular configuration.
So this is an example of what I was talking about before, right? Because essentially, instead of saying that each qubit is, a real number, you can add the unobservable phase to it. So you're creating a little clock, as Feynman would say, basically for each place, and you can describe it in sine cosine terms, or the I theta. So you basically have a lot more degrees of freedom to play with here.
Yes, exactly. Very nice. Very nice. And so this again shows you how this modulus squares, or the squares of the entries, correspond to some physical thing, right, that you actually observe under measurement. Okay. But look, there's many more, okay? I told you the first 2, but there's many other encodings that people have, not even on this list. The point is, how do people in quantum machine learning know which one to choose? This is the first step in your whole algorithm, in your experiment, right? That you're trying to gain information from. So this matters. If you choose the wrong encoding, or not the wrong, if you choose an encoding, that influences the rest of your algorithm, maybe in ways that you like, or maybe in ways that are not helpful. And what do I mean by that? There's things to consider. People have to consider, hey, how many qubits are required in this encoding? Remember the two examples, one required 4 qubits and one required 16. So if your encoding needs like 10 million qubits, but you don't have a quantum computer in 2026 with 10 million qubits, then you can run simulations, but maybe you can't do that. Of course, qubits are very sensitive as well to the environment. So the more qubits that you have, the more challenging that could become. Maintaining their sensitivity also doesn't require a lot of gates to implement. So a quantum gate is unitary. Remember I told you the circuit is these tensor products and compositions of unitaries. So those are called gates. A laser pulse, that's an example of a gate. So the more sort of laser pulses you're implementing, the longer you need to retain the state of your qubits, which could be a challenge because they're already sensitive. So if you have a lot going on in your algorithm, you have to think of that too. It's maybe better to have something that has fewer number of gates. Another question.
Can we actually say how many possible encodings there are?
I don't know. I don't remember what the exact number is right now, but the point is, people.
It's just a combinatorics question, right?
No. It's not a combinatorics question. There are other ideas that are very creative. So it's not just kind of like these are the only choices that we have, but there's different recipes or instructions that people are coming up with that are pretty creative. The ones that I see often in the literature are maybe smallish in number. And because I'm being recorded, I'm a little bit hesitant, but maybe like there's 10 that are out there, and I've listed.
Then if we don't have, if it seems like we can't actually give the number of possible encodings as a combinatorial object like cardinality or something like that, then do we really know a definition of what an encoding is, a quantum encoding is?
So I'm defining an quantum encoding to just be, so I guess there is technically an answer.
Yeah, it's a function, right?
Function from your set to your Hilbert space. So if your set is finite, if your Hilbert space is finite dimensional, okay, maybe you can think about that. But I think the point is many of these functions are not useful.
So it's the cardinality of your Hilbert space to the cardinality of X.
Yeah, but the cardinality of your Hilbert space is infinite, right?
Yes, but there's infinite combinatorics.
I wanted to tell you, Tai-Danae, Matt is our non-standard analysis expert, so he's very comfortable with infinities.
I'm not. So, okay, we can talk later then.
And logic and set theory, the infinite combinatorics is fairly straightforward for mappings like that.
Yeah, I appreciate that.
But do you require them to be one-to-one? That's part of my question. If it's an encoding, do you require that function be a one-to-one function?
Okay. I'm gonna have some other requirements.
That'll make a difference in the upper bound on the number of possible encodings.
Okay, absolutely. Well, it's gonna get even more hairy in a couple of slides.
Okay.
Yeah. So of course, that's what we want to think about. So that's what's on my list, right? Things to consider. I'm talking about physical stuff. I do want to mention this third point. How hard is it to simulate this whole thing on a classical computer? If you can easily simulate a quantum algorithm on a classical computer, there's no advantage, right? So you want to choose things that are hard to do classically, because the whole point is exploring whether quantum computers are even offering an advantage. But another question you could ask, which I like coming from mathematics, does your encoding preserve or destroy structure in the data? So in other words, informing your model about some structure that your data might have is going to restrict this large number of possible functions that exist a priori, right? Which then simplifies your search because you're kind of narrowing down the function space over which you're searching during your parameterization. So I think maybe the more information you give to some extent could, well, this is called an inductive bias, right? So it could simplify the search and improve your results, maybe be better efficient, be smarter about your algorithm. Like work smarter, not harder. And this is what I want to talk about. Maybe I'll just give a high level overview of this because I know that we're running close to time, but this is where the category theory comes in. Let me just kind of tell you quickly what I mean by structure, and I'm particularly coming from mathematical perspective. Think about this. Remember amplitude encoding, the one with 4 qubits? What did we do? We basically took a vector in Euclidean space and we normalized it. So in R2, if I'm just working in 2 dimensions, even just say with real numbers, if I have some points in R2, amplitude encoding basically just sends them to the unit circle. But look, if I'm interested in things like, clustering, for example, where I want things that are similar to be close by each other, then I have to think about distances. So distance is an example of mathematical structure. So look at this. If I do this amplitude encoding thing, beforehand, the green square and yellow diamond are close together, but after normalization, they get farther apart from each other. And that's not good if I wanted similar things to be close to one another. Maybe like dogs are here and cats are here and whatever. Also, I have a pink triangle and a purple triangle that originally were far away, but then amplitude encoding brings them close together. So the point is metric structure. Distances are an example of mathematical structure in data, and amplitude encoding is an example of encoding that doesn't care about that. In fact, it destroys it. So metric structure is something that mathematicians or people in QML may want to think about. Here's the point. Under this perspective, my data set is no longer just a set. It's a set equipped with a metric, right? It's a metric space. My Hilbert space is no longer just a set or a Hilbert space. It's a Hilbert space equipped with a metric. So I have this metric that I'm carrying around, and maybe I want to find an encoding that, either preserves distances or at least doesn't increase them or destroy them in a way that's not manageable, right? So this actually is a thing people study. It's called quantum metric learning. For the sake of time, let me move on to another kind of structure, symmetries. If I have an image, I have translational symmetry. If I shift each pixel to the right by 2, this is still a coffee cup. Okay, so I have group theoretic structure that I may be interested. Data may have symmetry. Maybe there's some group action involved, and I would like my encoding to respect that group action. Maybe I want it to be equivariant with respect to that. And so this is also a thing that's well studied. It's called geometric quantum machine learning. And so maybe there's other kind of structures. We talked at length about information theoretic structure. I really appreciated the question that led to that. Maybe I have something like mutual information between the pixels, and I want that to somehow be preserved, or I want to understand that in the quantum analog of mutual information under the encoding. Maybe I have topological structure. Maybe my data set has a topology equipped with it, and I'm interested in things like topological data analysis. So quantum topological data analysis is a thing. And so maybe I'd like my encoding to be continuous with respect to that. Of course, there's smooth structures. Maybe I want to think of my data set as a smooth manifold, and I'm going to analyze differentiability properties later on in my algorithm. So maybe I want my encoding should be a smooth map. So here's finally where the category theory idea kind of comes in. It seems we want to consider several ideas at once, right? And I think you see what I'm getting at. Initially, of quantum encoding, we defined it to be just a function, a vanilla flavored regular old function between 2 sets. But the point is, for some problems, you may want to equip your sets with metrics, in which case you'd like the encoding to not just be a function, but to be a function that's compatible with the metrics. Maybe it's distance non-increasing. Here I wrote embedding Lipschitz, whatever. Or maybe you're dealing with a problem and you have symmetry. So there is some group that you identify and you look at an action of that group on your set. So your sets are no longer sets, they're G sets. And maybe you'd like your encoding to be a G equivariant function. Maybe each of my sets is equipped with a particular topology. I want my encoding to be a continuous map. Maybe each of my sets are actually equipped with smooth structures, and I want my encoding to be a smooth function. You see where I'm going? There's a theme. In each scenario, we are interested in sets equipped with extra structure. And an encoding is a function between them that preserves or is compatible with that structure. So I'm being really explicit here by saying, okay, I have a set X and now I'm tacking on a metric D in one case. Or I have a set X and I'm tacking on a group action alpha. So I have a set and then some. Or in topology, I have a set X and I'm tacking on a topology tau or something else, right? So each of these worlds, of course, is a category. Each of these worlds of structured mathematical objects is a category, the category of G sets, the category of metric spaces, the category of topological spaces. So since this is just where we're living, we can just think of the QML encoding problem from this lens. And again, I'm going to just reiterate what I said at the beginning. This is not, research. The culmination in the next 2 minutes is not, and here's the encoding to use, but it's more just, here's how a category theorist might think about this. So a category theorist might think about this design setup as follows. All right, remember the main question. Does a particular encoding preserve mathematical structure? What does that mean? Okay, what it means is, I'm just summarizing now what we've observed. You start with plain old sets. You have a data set, you have a Hilbert space, kind of forget the Hilbert structure, just think of it as a set, right, of vectors. Then you add structure to your sets, right? You're adding a metric to the data set, you're adding a metric to the Hilbert space, or whatever structure it is that you're interested in for your particular problem. So you're moving from the category of sets to a totally different category now, up top. In the example I have, it's the category of metric spaces and what are the morphisms embeddings, for example. But these two categories are related. They're certain related. One, how do I get from here up top to here? I just forget the metric. Forget, okay? But what's the goal? The goal is, what does it mean? I want to find a structure preserving encoding. That means I want to determine, does there exist a function, just a plain old function down below between the sets with the following property? With the property that there exists a morphism in the category up top, so that when I forget the structure, like I apply the forgetful functor that goes from top to the bottom, I land on that original function that I started with. So does there exist a morphism that equals the original function after forgetting this structure? If so, then this morphism up top is my desired encoding. So that's kind of how you can think about it categorically, right? Maybe there's many embeddings or many morphisms in my category of structured objects, but I want to know, after I forget all of that structure, does that coincide with this original function that I'm working with, that I'm asking, hey, does this preserve structure? So, category theory has nice language for this. So I think that the perspective that we're offering is, okay, a quantum encoding, these functions, preserve structure if it lies in the image. That's just what I was saying on the previous slide, of a faithful, forgetful functor from your category of, structured mathematical objects to the category of sets. So, and this is nice because this is exactly this restricting idea. There's so many possible functions down below, right? But we're restricting those that we're interested in by framing it in this category theoretical way, right? We're only interested in those functions that satisfy this sentence on the top of the slide. So that's helping you simplify the search for a good encoding. So that was the title of this talk. What is a good quantum encoding? If you're interested in structure preservation, a good encoding is one that preserves structure. How do you think about that through the lens of category theory? We've just described it. The encouraging thing to this, you might say, wait, are you just repackaging known stuff in new, in category theoretical language? Like what does that bias? I'm very encouraged that category theory has played a foundational role in the development of things in classical machine learning and data analysis, like topological data analysis. If you read the original paper, it's like real algebraic topology with serious category theory, which is really cool to read. Also, UMath is a nice data dimension reduction algorithm. It's actually based on David Spivak's fuzzy simplicial sets, which I think is cool. So Leland McInnes and another co-author are the developers of that, and category theory played a cool role there. And so I think just knowing category theory's track record, at least in data analysis of this kind, maybe could provide, additional motivation for thinking of this QML problem through this lens. And I think it's just nice that I get a chance to talk about this. I appreciate the invitation here because maybe the more mathematicians know about this problem. I went to this conference last year, this QTML conference, where this is the state of QML is like, the main focus of the entire week. And maybe there were one or two other pure mathematicians there, in this huge room. And so I think maybe the more tools that we have from the realm of pure mathematics or other disciplines, I think could be really helpful for this field, which is still new and growing. And so who knows what might happen next. I like this. I'm going to close here. So I really appreciate this quote from a team at Xanadu. And this was from 2024, more studies that focus on questions of structure and data are crucial for the design of meaningful benchmarks. So if you're even going to do tests to know if, to Daniel's point earlier, like, is this even a good thing to do? Well, you should be a little more principled, right, in how you think of it. So I really love that they're saying we should ask, hey, what mathematical properties do real-world applications of relevance have, and how can we connect them to the mathematical properties of quantum models? So I appreciate that sense that thinking of things more mathematically and more formally, could be a promising direction. So I think I'll end here. Thank you all.
Thank you, Tai-Danae. Let's see. Hold on. Let's do the React thing. Yeah. So this was awesome. And you managed it despite our interruptions and our taking over.
Great.
Well done. I knew you were a fantastic speaker.
I didn't live up to my usual
standard
of making you not make it.
Right. No, fantastic.
Pass the test. Good.
And without going into too much technicalities, I mean, I'm just talking at the high level in terms of the process for the relatorium. This is a great example because you taught us some math. We talked about some math, and you talked us about ideas and opened windows, which is exactly what we want to do here. So well done. Yeah, I wonder, I've spoken more than enough here. I wonder if others have comments, questions for Tai-Danae for the next few minutes, if she can stay with us.
Just like to say something. I'm not a mathematician, but the higher level at which you were addressing complexities, that's the best way that I can capture what you're talking about. In terms of real world relevance, I think that this way of looking at complexity and how to calculate the nature of the complexity and how to translate and communicate certainly applies to the complex of social problems that we're dealing with. And I think it becomes especially encouraging, just looking at it at a high level, that there is a way of thinking about complexity that ultimately is not overwhelming. And some of the social divides that we have related to class, gender, social justice, etc., so far has proven to be perplexing to our policymakers. But I think conceptually, mathematicians can come up with models and visions of how to engage this complexity in non-political terms. So your work is very exciting. I will follow what you're doing as best as I can. As you were speaking, I just got flashes and intuitions as to how some of these concepts and processes might relate to solving social problems. So I really enjoyed your talk. Thank you.
Thank you for that. I appreciate it. Thank you so much.
Yeah, and I wonder, in fact, these ideas, even the idea of entanglement and the difference between entanglement and correlations or classical probabilistic, joint distributions and so on, what difference they could make as conceptual tools for understanding social interaction, social sphere. Because, it is arguable that part of the challenges in understanding and managing the social environment is because of the lens through which we see it. I mean, Eugenia Cheng has made this point repeatedly and very effectively, but even notions of, dependencies, these contingent dependencies that go beyond pairwise interactions that essentially are all the correlations can tell us, might by itself be a way forward. So a way of thinking in quantum terms, or in the terms that we learned to develop by seeking to understand quantum phenomena, but to other environments, like the questions of computation that you were talking about, or questions of, social structure, understanding. I think developing such analogs, such sort of metaphors, if you will, is very much an interest of ours here at the Relatorium. I think you contributed significantly even in this respect, that you gave us new words to think about using for describing complexity. Just like Grady said, I mean, seen entirely only even as a contribution towards how can you speak intelligibly and in a refreshing way about things that are often left having this aura of incomprehensibility, around them, like entanglement, like to be so willing to engage with that and seek new ways of describing it. So thank you very much. I think that was masterfully done. I'm interested in the, obviously you're very interested in the categorical kind of angle to this. I almost earlier on, one of the things that you were saying struck me as also categorical, and perhaps even in a related way, in that this going from, let's say, classical computational modalities, classical ML, to quantum ML, the process itself, is a categorification of sorts. In other words, it involves mapping, creating, mapping certain relations, like manipulations of certain certain objects represented in a particular way, to a very different representation. I mean, certainly what you talked about was the first leg of that, right? Like the mapping of the objects, right? What are the objects that we want to operate on? But the whole process of computational thinking, right? Of like how we think of, problem solving, let's say in mathematics, right? Like we encode a problem in a particular way. We try to manipulate it, map it into standard forms and so on. Like this is a classification problem essentially. And then extracting, some sort of yes or no answer, splitting it up, in other words, in a sequence of a decision tree, if you will. I mean, mapping that into another structure, that the structure itself, that formalism isn't the thing itself. It's just a representation of the thing. And so in the quantum realm, we have these matrices, right? And we have tensor products. We have an algebra, essentially, right? A multilinear algebra on complex vector spaces that we do this, if you in Hilbert space, right? Essentially does the same thing, or it may do more things, but it does an analogous thing. So the relationship, is categorical. And of course, like all categorical things, is composed by other categorical mappings, like the one that you were talking about, the encoding bit, which admittedly gets too little attention. Even, even though I've been teaching this for a few years now, I only knew of 3 of the ones that you mentioned. I only really talk about one to my students. So this very question is, but even more broadly, like what does it mean to develop different models of computation, right? Rethinking computation in terms of linear algebra operations, for example, or embeddings in higher dimensions. Rethinking of topological data analysis that you were saying, but in terms of, algebraic operations, right? Rather than, I mean, as a mathematician, this is very attractive to me. that you're getting more to the heart of the matter, it seems, with this categorical thinking than being too tied down to a particular formalism.
So I had a couple of questions that are more specific to your final problem. So for example, when you started with a set and now with X being just a set, and then you go to the metric, that is related to my question about how many quantum encodings there are, because whenever you restrict the notion of a quantum encoding to a functor where you put a structure on X, you then, when you have a concrete category like that, you go from more possible morphisms, the abstract functions or set theoretic functions, to less, because it may not be less in cardinality because you have infinite sets, but it is a proper containment relation in some cases. And then maybe I misunderstood you at the beginning, but I think you said that you came mainly from category theory rather than quantum mechanics or something like that. So you may know the answer to the following question: are there categories A and B for which there is no functor from A to B? And presumably in abstract categories, you could get those. And if that's the case, is it possible for the category A and the category B to be concrete and B to be the category of Hilbert spaces? And then there's and then the category A that you're thinking of, that's describing the what are the features that you want to capture in your quantum encoding, right? When you put that category structure on the set X or whatever, then is it possible to give an example that proves that there's certain situations where there's no such thing as a quantum encoding? And that would be a purely category theoretic question, I think, right? Either it's a concrete category theoretic question, but if you broaden the perspective to include abstract categories, that's a very interesting other setting, I think.
Yeah, I appreciate this question, and I like the flavor of going a step beyond just my presentation, which is, hey, here's how to ask this question category theoretically. And I think what you're getting at is, what's the utility of that? Does the category theory inform us of something about the problem? I need to think about your proposed theorem a little bit better. But that would be the hope of the next step for this. I mean, there's actually a few directions in which my co-authors are even thinking of taking this now. But we didn't have anything conclusive here yet because we just kind of wanted to get the perspective out. But I think this is exactly the point of, why would we reframe this in terms of things that category theorists think about? Yeah.
And you formulated it in terms of a morphism from X into H. But if X is not a Hilbert space, then in some sense, there's no morphism from X into H.
Sure, their types
in the category of Hilbert spaces.
Absolutely.
So you have to forget the structure on the Hilbert space to even get started.
Yeah. So well, to be concrete, but so both X. So if I think of my Hilbert space, then I just kind of forget the linear structure. So it's just a set. The data set and the Hilbert space are both objects in the category of set.
Right.
And then I tack on extra structure like a group action or a metric. Now both of those objects are G sets, or both of those objects are now metric spaces or topological spaces. So those are my categories involved. It's the category of sets always. and the Hilbert space lives there if I just kind of forget the Hilbert structure. But then there's another category in which I'm having a conversation, the category of structured objects. And now, you know, my new improved data set lives there because now I'm doing it as a smooth manifold. And my new improved Hilbert space lives there because now I'm doing it as a smooth manifold. And the functor is between those two categories. And it always goes down to the category sets. But I love what you're asking. Now that you know you have, or if you're looking at a faithful functor, forgetful faithful functor, what can you say? Like, tell us some theorems and what does that give us? So
this is what I had in mind as well. You found better ways to describe what I was striving at, this kind of codification, sort of meta level categorification, where basically we in the very process of adding structure and modding by a structure, you know, and combining structures, composing structures, if you will, is itself a categorification of the action that we do on the previous structures. You know, we start with the simplest one, set, which is basically classical logic, you know, bits. And then we make it into qubits by allowing it to have, you know, maybe the operation is you give it an unobservable degree of freedom, maybe, you know, cross S1 or something like that. I don't know. And then I'm just like abstracting away from the specific example and saying, this is what we do. And then we have, you know, two different distinct ways of adding structure. And then how do they come together into something that's compatible, let's say. You know, so I don't know enough category theory to formalize this, but I have a feeling that it's the kind of question that becomes possible, just like Matt is saying with your approach, Tai-Danae. I think like to embed this question in this much larger space of possibilities. So,
yeah, I like it. Yeah.
Well, there in the in fact, if you go to the category of categories, then this morphism from X into H can be thought of as a functor itself. And because morphisms between categories are functors. So I'm not sure if something nice can come of that, but you go to higher category theory that way, don't you? Yeah.
Yeah. Lots to think about. It's great.
That's another way to infinity, Matt.
Yeah.
Definitely.
I see where you're going.
All right.
Yeah.
Well, thank you, Tai-Danae.
Thank you.
Thank you so much for your time, for staying so long and engaging with all these, you know, rather, you know, our simple questions, you know.
I want to point out that I was so glad that you were going to talk because I watched all of PBS Infinite series. And I was so disappointed when I found out that when I first started watching PBS Infinite series, it was mostly over.
Oh, well,
because I got introduced to it through YouTube. So
yeah, that was a while ago.
Yeah, I really enjoyed your predecessors and you in those series. It was very nice presentations of stuff.
Thank you. I really appreciate that. Thanks so much. And thank you for having me today.
Thank you and good luck.
Thank you for joining us.
It's exciting.
If you want to join us more frequently, please do. Yeah.
Great. Thank you. Yeah, I'm on the mailing list, so I appreciate that.
Excellent. Yeah. Bye-bye.
Okay, take care, everyone. Bye.
Bye.
Thank you.
Hi, everybody.
Just ended the stream.